very briefly go over what happens at a finite temperature. That is, of course, within the area of statistical physics, but since we really do not have that much time to discuss the fundamentals of statistical mechanics, and you will be taking it, or you have taken statistical mechanics anyway, so I'll just give you a brief discussion. So certain things you'll just have to believe me. Like the first, let me just write this down. So what happens at finite temperatures? You see, we have not even defined a temperature in this class, but we'll have to introduce it in some ad hoc way along the way. Okay, so whenever you have the temperature, you have to worry about the statistical features associated with the system. And there is this quantity which is known as the entropy. It is defined through probabilities, and the way you define it is minus sum over I pi ln of pi. Okay, so this is the amount of information that you do not have about the system. Okay, it's sometimes called the missing information function. If something is statistical, then that means you don't know everything about the system. Certain things happen at random, and because of that, you have some missing information. Okay, so how do we introduce the probability into our picture? Well, at a certain temperature, certain states, okay, I will be drawing the same figure here hundreds of times. So this is the kx, ky, kz state, kz axes, and then I have these states. Okay, so these states have energies EI. Okay, so I'm going to now label these energy states. So I'll have some set of energy states. So let me just schematically put it like this. I do not care about their order in the K space. Statistics does not really care about the actual K values. The statistics depends mainly on the energy levels and their occupations. Okay, so I have these energy states, and these things have energies. Let's just call them, I don't know, epsilon 1, epsilon 2, epsilon 3. So in general, epsilon I. Okay. And then we also need to keep track of whether they are occupied or not. So we have to look at the occupations, and I'll associate a number N1, N2, N3, etc., and I with all of them. Okay, so and I'll also separate the spin and the space state so that every state here is unique. Okay, so if it can have the same energy but downspin, same energy but upspin. Okay, so they will be different states if they have different spin values associated with them. Okay, so I can have particles with certain occupations. Now, if they are fermions, the occupation number can be, okay, so for fermions, any one of these ni's can be 0 or 1, okay? Either unoccupied or I have a particle there. Okay, so the spin degeneracy, I am counting those states as separate, okay? For bosons, okay, there's no such restriction. The ith state can have 0 particle, 1 particle, 2 particle, all the way to infinity. Okay, so I can have as many particles as I like in the boson system. Okay, so what are these PIs then? My interpretation of PI is going to be PI is the probability. Okay, so PI, okay, probability that state I has occupation Ni. Okay, so PIs depend on what n's are. Okay, so PI, so what that intrinsically means is that my PI depends on Ni. Okay. All right, so in order to find these macroscopic quantities, there's a standard procedure. What you do is you try to maximize entropy, but you also have to put some constraints during that maximization so that you get reasonable results. Obviously, there's more than one way of doing this. Okay, but obviously, if you take the statistical physics course, then okay, you know that you can calculate this in various different types of ensembles and get different methods, but everything gives you the same thing. Okay, so what we do is we are going to maximize, okay, entropy with some constraints. Okay, so the quantity that I want to maximize is this sum. I'm lucky there with the pens. Okay, so sum I P I ln P I with various so I can just differentiate this with respect to PI and try to obtain the extremum, but there are constraints. First of all, let me first write this, 1 minus some PI. Okay, so constraints I can put in using Lagrange multipliers. Okay, so I put here a Lagrange multiplier, let me call it lambda 1 because I'm going to actually have other constraints. So if that's the only constraint, I just maximize this, okay, with respect to P, but then I also differentiate with respect to lambda 1 and set that equal to 0. That automatically gives you this constraint, okay? So what about others? So I want to also make sure that, okay, I get some average energy. Okay, so what is an average energy? Well, so maybe I should write it over here. What is the average value of the energy? Well, it depends on the occupation probability of the ith state, okay, multiplied by the occupation number there and the energy of the ith state. So I sum this over all possible values of the probabilities. Okay, so I'm going to get something which looks like that. So P, I, N, I, E, I. Okay, so this is the expectation value of, so I want the expectation value of energy to be equal to capital E. And furthermore, I want to keep track of the number of particles because if I just try to optimize the probability, you see it will generate lots of n's in the system, but I also have some number of particles in the system. Okay, so that will be another lambda, so let me call this lambda 2. This one is lambda 3, so that will be n minus pi ni. So you see the number of particles is not fixed, but their expectation value on the average, I want it to be equal to some capital N. Okay, so the average value of N is just I, pi, and I, right? So I want that average value to be equal to some certain value, number of particles that I have in the system. Okay, so let's just go through this. So I differentiate this with respect to any one of the pi's. So if I choose a certain, say, p, I don't know, pk, then what do I get? So I take all of this and differentiate it with respect to one of the probabilities, any one of the probabilities, and I set it equal to 0. Okay, so that's how I find the extremum. So that picks out only one of those probabilities over here. So it's going to give me minus ln pk, derivative with respect to that, minus 1, okay, minus lambda 1 times what? That's it, right? pk will give me just minus lambda 1. And then if I look at this, plus, well, minus, because of this, minus lambda 2 n k e k, and minus lambda 3 n k is equal to 0. Okay? And then this says that I can just look at what this is going to give me. Let me move the logarithm to the other side of the equation and exponentiate. So pk is going to be equal to e to the minus 1 plus lambda 1. Okay, minus lambda 2 nk ek minus lambda 3 nk. Okay, so I get something like this. Now it's time to play around with lambda 1, lambda 2, and lambda 3. Okay, you see each term here, which is multiplied by an associate Lagrange multiplier, that Lagrange multiplier adjusts the average here so that you get something. You see, at the end result, you don't have any capital E or you don't have any capital N. Okay, those things you have to obtain from this probability by adjusting lambda 1, lambda 2, and lambda 3. So when you are adjusting lambda 1, for example, you are making sure that this, is satisfied. But what is this? This is just normalization of the probability, right? So this says adjust lambda 1 so that this probability is normalized. Okay, so this whole thing here is a normalization constant. Okay, you adjust this lambda 1 so that things are normalized. Now, lambda 2 is a variable which you adjust so that the average energy is something that you need, something that you want. Okay? And this lambda 3 is something you adjust so that the number of particles is equal to n. Okay? So these things, by going through some comparison with what you get from ideal gas, etc., you develop a theory which identifies these things with certain physical quantities. For example, this lambda 2 is really something that you essentially define as temperature. You see, this has to be unitless because it's being exponentiated. So lambda 2 must have energy, must have unity, so 1 over energy. So that thing is 1 over k Boltzmann times temperature. Okay, so how come I can write that? Well, that's a long story. Okay, so reaching that in some sort of rigorous way would take a few weeks of discussion. So we are just going to define temperature this way. Okay, so it just is the term that multiplies the Lagrange multiplier associated with adjusting energy. So by adjusting this t variable, by adjusting this lambda 2, you can find out what energy is. Okay, so energy is functional temperature. Okay, this lambda 3, okay, so that is something that adjusts the number of particles. And what we are going to put in its place is, okay, it's going to be mu, like the minus sign, the way this is defined, minus mu over kBt. Okay, so this mu is called the chemical potential. And is associated with the energy that is needed to change the energy of the system by when you add or remove one particle. Okay, so with that, let's rewrite that equation. So probability all right. So let me just rewrite that. Pk, which will be function of nk, okay, because that's our definition for the probability that the kth state will have nk particles, is going to be equal to e to the, well, some normalization constant. Let me just call it, well, I won't call it anything else. Let's keep things simple. 1 plus lambda 1. And then I have e to the minus nk ek or k Boltzmann t. And in fact, let me just group everything together. Since the other term is also an nk, let me write it as minus mu over kBt. Okay, so that's what my probability of having nk occupation in the kth energy level looks like. Okay, let's just see what happens. Yes.
Why are we looking at having k elements in the kth energy state? Like, why the same number specifically? Because in the electron gas, we in every energy state, the number of electrons that we could have was proportional to the square root, cube root of the state itself.
No. In the case, in the previous case that we discussed for the Fermi gas, the occupation of the states nk was either 0 or 1. Okay, so in the previous case, when we looked at this stuff of occupation stuff, the nk corresponds to whether the state is filled or not. Okay, so over here I have an nk, actually in this picture it's 2 because of spin degeneracy, but nk over here is 0. Okay, so now we are going to get really possibly different values. Okay. All right, so we have that. We now have to specify, restrict ourselves to either the fermion or the Bose-Einstein. Well, maybe I'll just go one more step. So let me look at what is the average value of particles in the Kate state, okay? What is the average value of the occupation? So how do I do that? Well, I can just take this pk, actually if it is normalized, and sum over all possible values of nk. If it's normalized, I don't have to do anything, but I still need the normalization here, so I'm going to put nk, pk here, so that everything is automatically normalized. So that means I'm going to get a sum over all possible occupation possibilities. Okay, that's where the fermion boson case makes a difference. For fermions, this is 0 or 1. For bosons, this goes from 0 to infinity. Okay, so this is going to be e to the minus 1 plus lambda 1, e to the minus n epsilon k minus mu over kbt divided by and multiplied by nk, most important factor. Okay, nk, the same thing without the nk, e to the minus 1 plus lambda 1, e to the minus n, this is nk obviously, ek minus mu over kbt. Okay, so these terms cancel. Their whole purpose was just adjusting the normalization anyway, so I'm carrying out the normalization this way. Okay, now I have this equation. Let me leave this alone and go to another board and look at the fermion case and the boson case separately. All right, so for fermions, what is the average occupation value? Well, over here I have nk, okay, so this corresponds to the summation nk value 0 or 1, okay? So if I take nk equal to 0, that gives me 0. Nk equal to 1 gives me e to the minus 1, so ek minus mu over k Boltzmann t divided by, okay, the same thing except that now I don't have an n multiplying it, so it's going to be e to the n equal to 0 gives me 1, right? So n equal to 0 is going to give me 1 plus e to the minus, same thing, k minus mu or kbt. So just multiplying by the positive of that, that's going to be 1 over e to the ek minus mu or kbt plus 1. Okay, so this is called the Fermi distribution. Let's just see what it looks like. Okay, so if I plot Nk as a function of Ek, okay, so you see I have this factor mu here. If Ek is less than mu, okay, then this is going to be e to the some negative number, and potentially it's going to be small. Now, I sort of hinted to you that this KBT for the practical systems that we are interested in is actually quite low. Because that's quite low, this is going to be a large number. If Ek is less than mu, it's going to be a large negative number, which means this is going to be very close to 0. So for values of Ek less than mu, I'm going to get practically 1. And then when Ek is equal to mu, you see then this is 0, and then I have e to the 0, which is 1. So when this reaches mu, it's going to be 1/2. Okay. And then if Ek is larger than mu, then of course this is going to be a large positive number, and this will go to 0. Okay, so it will do something like this. Okay, so now you see at 0 temperature, we are going to get this. Okay, so that's the t equal to 0 case. And that tells us that everything is up to this energy is full. Everything after that energy is empty. But that's from the picture that we have studied. This mu now is something that we identified as the Fermi energy. Okay, so for the Fermi gas, we have the chemical potential equal to the Fermi energy, and we get a distribution which depends on temperature. Okay, at very high temperatures, okay, thousands of Kelvin, tens of thousands of Kelvin, you are going to get a bigger smear on the original function. But for things like metals at room temperature, this is going to be very close to actually the t equal to 0 curve. Okay, so if you are interested in finding the total number of particles, then of course you have to, okay, in fact, let's just write that down. So n equals all of these things, okay, so I just sum over all of these nks over all the k levels. But how do I sum them up? All these k levels, now I need my factor. Okay, so I'm going to need that factor, which was what? K squared dk volume over pi squared, right? I erased it, but I think that was it. Okay, so this is the density of states, if you like, in the K space. And I multiply it by this Nk, which is going to be e to the Ek minus mu over kBt plus 1, and integrate it from 0 to infinity. Because now I have to, so at 0 temperature, we know how to do this integral. We already did it, okay? That was an integral from 0 to Kf, right? But now, if for a finite temperature, there's no sharp cutoff at Kf, so I have to include the whole function, okay? This integral is doable, but gives you a special function. So it was analyzed by Riemann and others, are related to the zeta functions and such things. So, okay, we'll not say any more about that. All right, what are we doing on time? Okay, so let's also look at what happens in the boson case. So let me keep, yes.
Why didn't we take nk equals to 2k squared?
Yeah, okay. We should really multiply this by the spin degeneracy, which I forgot. Okay. So, no, spin degeneracy is already there.
Not in there, but in the above averaging.
No, in this case, okay, for this case, I have assumed that each one of these states, spin up state and spin down state, are separate, discrete.
Separate.
Okay, so so that gives you something which is normalized to 1. Okay, so otherwise, if you have a spin 3/2 state, for example, all you have to do is multiply this by 5 or 4. Okay, let's look at the boson's case. Boson's case is actually somewhat richer in the type of things that you can do. All right, so in the case of bosons, I have this nk, set of nk go from 0, 1, 2, 3, etc. There is no limitation on the number of particles that I can put into these states. All right, so these things, let's look at nk again, because that gives you a nice distribution. Nk is now going to be an infinite series. So I'll just write from this equation. There's an nk here, and there's a series without nk. But you can see that the form of the series is something like this. I have a summation, okay, with respect to n, which will go from 0 to infinity. And the form in the, well, the form in the denominator is something like e to the minus na. Okay, so it's the sum of a geometric series, and I can write down the sum immediately. What is this? I gave you a hint by saying 1 over something.
1 minus e to the minus a.
Okay, 1 minus e to the minus a, right? Now, to have the one with the n here, what I do is I differentiate with respect to a. Okay, so if I differentiate with respect to a, excuse me, okay, it will bring down an n. Which is exactly what I want in the numerator. So I have to do the same thing on the right-hand side. So it's going to be the square of the denominator. Excuse me. 1 minus e to the minus a squared. But now I have to differentiate the denominator, and there are a number of minus signs. There's a minus sign in front here. There's a minus sign which comes because I am differentiating this. There's a minus there, minus there. So there are 4 minus signs, which gives me a plus sign, e to the minus a, okay, derivative of the denominator. Check my algebra, please. Is this okay? I think it's okay. So let's put those down. So the numerator is something like this. So it's going to be e to the minus a minus what? ek minus mu or kbt divided by, okay, the square of 1 minus e to the minus ek minus mu over kbt squared. Okay, big denominator 1 over just one factor of this, 1 minus e to the minus ek minus mu kbt. Okay, so this will cancel one factor of that. So let me just, okay, and then I'm again going to multiply by e to the plus something so that I get 1 in the numerator and e to the plus now ek minus mu over kbt minus 1. So it's very interesting that you get basically the same thing, you see, that we have here, apart from a sign. Here I have a plus sign, there I have a minus sign. But that makes obviously a big difference, because here now you see this exponential can at some point be very close to 1. All right. Now we have a number of choices for this ek, because, okay, for the electron system, we just said, okay, it's the solution to the Schrödinger equation, so we have this h bar squared k squared over 2m type of behavior. For bosons, we have some nice choices. I can again have massive bosons. By massive bosons, I can have, okay, so what are the possibilities? So ek can be something like h bar squared k squared over 2m. Okay, so you see I have a m here. So these are bosons with mass. But there's a very important boson without any mass. What is it? Photon. It's a photon. Okay, so if I have h bar k, that's a different dependence. That's the photon. So whether I am interested in a photon gas or something like liquid helium, I have to put a different type of ek over there. Okay. So let's look at the massive case first. For the case when I have bosons with mass, okay, then I have this nk equal to, well, I'll be just rewriting the same expression in a sense, 1 over e to the, okay, h bar squared k squared over 2m k Boltzmann t. I forgot the mu. Minus 1. Now, you see, this mu, we said, which is the chemical potential, becomes related to the energy associated with putting a new particle into the system. Now, if you are at a high temperature, let me just qualitatively draw what these things look like. qualitatively as a function of this Ek, and K will now look something like that. Okay, so higher energy states will be less occupied than lower energy states. But so this is, let's call it high temperature. Now at low temperatures, okay, you have an interesting effect coming in. You see, I have all of these energy levels, and now as I am approaching low temperatures, the particles want to go into the lowest energy states, okay? And as they go into these lowest energy states, these states get really filled up. Most of the particles are now at low energies. But there's a problem with the K equal to 0 state. Okay, in the K equal to 0 state, which is the lowest energy state, ground state of the system, you are going to get, okay, it doesn't really have to be the zero energy, it's just the lowest energy, because you see energy scale is just relative. So if I look at the ground state energy, when this thing reaches the ground state energy, the cost of adding a new particle, okay, which is this chemical potential, approaches this very much, okay, because now you can put your new particle into this lowest state very easily. So this gets very close to that, to mu. In fact, they both approach 0, okay. So this number approaches 1, and you seem to get a divergence. Okay, what that means is that you cannot treat this as a continuum anymore. So if you want to find, for example, the total number of particles and such things, when we carried out the integral over there, we went, okay, without considering too much whether we can go from continuum to, from discrete set of K to continuum. But now we have to worry about that. So what happens is that this lowest energy state, okay, if you insist on drawing it at the continuum, this n of the lowest energy state contains a fraction of the total number of particles. So you are again going to get some particles in higher energy states, but this, okay, and 0 here means that a fraction of the total number of particles are in the ground state. And that fraction increases continuously, okay, until you get to 0 temperature, okay, so at T equal to 0, this N0 actually makes up all of the particles. You don't have anything left too high. And that's something to be expected, right? At 0 temperature, everything will go into the lowest energy state. But what's important here is that perhaps at sufficient low temperature, perhaps half of the particles in the system, in the microscopic system, are in the ground state, okay? So these things, depending on the details of the system, produce things like superfluidity and things like that. So this is called a macroscopic quantum effect, because it's now something that's visible, okay, to humans. You can see this superfluid doing interesting physical phenomena, and this effect is called the Bose-Einstein condensation. Okay, and these particles are now called Bose-Einstein condensates. So unfortunately we cannot go into any more detail, because that's now more materials and statistical physics content. But next time we'll look at the other case, the photon case, very briefly, and see what happens to that at finite temperatures. Okay, so I'll see you Tuesday.